Okay, so next section. You might notice that the previous section was 2.5, and now we're kind of going back to 2.4. It's complex numbers. That's because this section very much builds into what we just saw. In fact, it seems almost disconnected, but now that we know how to solve quadratics, we can say, okay, well, there's a special type of quadratics that needs a concept like complex numbers, and hence complex numbers are important. So here's an equation that in the last section we would have been able to solve. At least seems like we would be able to solve. First step would be we would subtract 1 from both sides, and then we would take the square root of both sides. But that creates an issue. We can't really take the square root of a negative number. There is no number in the real numbers that if you multiply it by itself, you'll get back a -1 or a negative number, any negative number for that matter. So we introduce this idea of imaginary numbers. And that allows us to solve this equation. So an imaginary number is a number whose square root is -1. So if you see I, that just means it's the square root of -1. And for that matter, if you square I, then -1 square root times the -1 square root gets rid of the square root, and you have -1. And really that's pretty much the idea of this entire section is it's going to build on this. Do we understand what I is, where it comes from, and do we understand what I squared is? So let's kind of dive into that. Now here's a question that we wouldn't know the answer to previous to imaginary numbers. We would have to stop and say there's no real solution. Well, what we can do with this idea of imaginary numbers is we can kind of split the -49 into two parts. And say, okay, I don't know what the square root of -49 is, but if I break it up, I know what the square root of -1 is now, and I also know what the square root of 49 is. Square root of 49 is 7, and square root of -1 is I. And then just as kind of notation, we typically write the number and then I, just like we do with variables. You usually put the number in front of the other. So I times 7 is technically correct, but the notation that you'll see most often would be 7i. Same type of idea with square root of -7. I'm going to break it up into two pieces. Now in this case, I don't really know what the square root of 7 is. And yes, you're allowed calculators in this course. So you might be able to find a decimal approximation, but I'd prefer you didn't. So we're just going to leave the square root of 7 alone and just say, well, now I know the square root of -1 is I. That's my answer, I root 7. Let's do one more example. So in this case, I have a negative square root of -4, exact same concept. I'm going to split up my square root into two separate parts, but we have to be careful. I'm not going to put that negative and have any double negatives cancel out or anything like that. I can't move a square root or a negative under a square root. I can't move a negative inside a square root outside of it. So I just have to leave that negative where it is. I know the square root of -1 is I. I know the square root of 4 is 2, so I get my final answer of -2i. Now multiplying and dividing. Normally, if we have positive numbers only, if I'm multiplying with square roots, I can just multiply whatever's under the square root and then take the square root. I can't do that with imaginary numbers, so I have to go back to that first step that we saw on the previous slide. I'm going to split up my negative square root of 5, and I'm going to split up my square root of -6. Well, we could write it out again and again and again, but we know square root of -1 is just I. So my first term is going to become I root 5. My second term is going to be I root 6. And now I can combine like terms. I can multiply whatever is under the square root to get root 30. And I can multiply the i's. That will get me I squared square root of 30. But we talked about at the very first slide, I squared is -1, and so we don't really want to deal with imaginary numbers if we can avoid them. So we know I squared is -1, let's go ahead and say that, and now we have a real answer. And notice how this is different if you would have just multiplied that -5 times -6, you wouldn't have gotten a negative square root of 30. So make sure you're doing this process if you're multiplying or dividing, or adding and subtracting for that matter. Now for this question, I don't have to break up the second square root because it's -1 already. So the second square root is going to be I. And if I split up that first square root, I'm going to have I root 9. So I'm left with root 9I times I. Well, the square root of 9 is 3. And I squared is -1. So I get -3. With division. same concept. Bottom, I don't have to do anything. I don't have to do any simplification. There's no square root. On the top, I have to factor out that -1. So I get -1 times the square root of 27 over the square root of 3. Now that I have a positive square root on top and a positive square root on bottom, I can go ahead and divide those. That's perfectly fine. I don't have to do any more work. So 27 divided by 3 will get me 9. And I know square root of 9 is 3. I know the square root of -1 is I, so I'm left with 3i. Now, complex numbers. Complex numbers is kind of encapsulates both real numbers and imaginary numbers. And so sometimes you could have a situation where you have 3 plus some sort of imaginary number, and that gives us this complex number. So by definition, a complex number is if you have a real number a plus a real number times an imaginary number, so b times I. And the cool thing about complex numbers is they follow all of the operations that we've seen: multiplication, division, subtraction, squaring. And anytime you do a complex number, you will still get a complex number out. So that's kind of why we talked about I squared being changed into something. There is no I squared in a complex number, but we know now that that's a real number. So we're going to always be able to simplify back to some complex number. The easiest form to deal with complex numbers is adding or subtracting. Because at this point, it honestly doesn't really matter what I is. We just treat it as though it's a variable. And so I'm just going to combine like terms. Well, 3 plus -4 gets me -1. -5i plus I gets me -4i. Ooh, I kind of skipped ahead a step. And then I'm just going to get -1 minus 4i. I guess what I should have explicitly said is that if there's a plus in the middle, you can just go ahead and drop the parentheses and then combine like terms. It's a little bit different if you have a minus in between your two complex numbers. So yeah, 4i is an imaginary number, but 4i is in the group overall of complex numbers. So my two complex numbers that I'm subtracting here are 4i minus 3 minus I. And if I'm subtracting, if I have that subtraction in front of my parentheses, my first step is to distribute the -1 to both things inside the parentheses. So my equation becomes -1 times 3 gets me -3, and -1 times -I gets me positive I. And now I can combine like terms just like I did previously. 4i plus I gets me 5i, and -3 doesn't combine with anything, so I'm just left with -3 plus 5i. While I'm thinking about it, yes, technically the order doesn't super matter. Like if you were taking a test and you wrote 5i minus 3, that works. It's just a good convention to say, okay, I'm always going to have my real number first and my imaginary number second. That's typically how complex numbers are written. Multiplying complex numbers, it's again almost as like I is a variable. We just have to account for that fact that we actually know what I squared is. So if I squared shows up, we have to deal with that. So let's see that in practice. I have -4i times 5i. If I multiply those together, I get -20i squared, just as though I was a variable. But I know now that I squared is -1, so I'm going to replace that I squared with -1, and I'll get -20 times -1 gets me 20. Now I'm just going to use the distributive property. Again, I'm going to treat it as though I is just a variable. So I'm going to distribute my 5 to both things inside the parentheses. So 5i times 2 gets me 10i. 5i times I gets me 5i squared. I'm not going to resolve I. I'm just going to leave that as an imaginary number. That's perfectly fine. I'm going to take my I squared. I'm again going to replace it with a -1, and 5 times -1 gets me -5. Now, again, if I was just following the order of what was before that finals equal sign, I would be left with 10i minus 5. But if we want to write things properly as a complex number, we write the real number, then the imaginary number. Here I'm going to, the technical term is distribution, but generally people know this as foiling. I'm going to FOIL out this equation. So I'm going to do 2 times 6, 2 times -I, 3i times 6, and 3i times -I. And then I'm going to multiply all of those terms out. So I'll get 12 minus 2i plus 18i And well, I went ahead and replaced the I squared with a -1. So -3 times -1 gets me 3. And now this is just an addition problem. I'm going to combine my real terms. 12 plus 3 gets me 15. And my imaginary terms, 18i minus 2i, will get me 16i. This question is almost the exact same process. It's just a common pitfall. One of the most common mistakes I see throughout my entire course is when something like this shows up, when we see a binomial 3 minus I squared or x plus 2 squared, and the squared's outside. Quite often people distribute that square to the 3, distribute the square to the I, and call it a day. If you see it like that, what a square means is you multiply the number by itself. So you actually have to rewrite that as 3 minus I times 3 minus I. So watch for that. That concept's going to show up a lot. It's going to be easy to make that error, so kind of get that in your heads now of saying, oh, okay, I'm going to just rewrite it twice anytime I see that square outside. And then again, I FOIL. 3 times 3 is 9. 3 times -I is -3i. -I times 3 is -3i. And -I times -I gets you positive. Now, this is a very common problem that I see throughout the course. When we have something like this, when we have a binomial squared, what students typically, well, not typically, but often do is they take that square and they say, okay, I'm just going to take the square and put it on the 3. I'm going to take the square and put it on the I, and then I'm just going to go ahead and square each term individually. That's not correct. That definition of squaring something is you multiply that thing by itself. So anytime you see something like this, a parentheses and a square outside, just rewrite it twice. That's what you're going to do. And then you're going to FOIL it out just like we saw in the previous example. 3 times 3 is 9. 3 times -I is -3i. -I times 3 is -3i. And -I times -I is positive I squared. Now I have to resolve the fact that I is going to be -1. And then I can combine like terms. -3i times -3i minus 3i gets me -6i. And then 9 plus -1 gets me 8 minus 6i. Now finally, I'm going to go through this one a little bit more quickly because it's actually the exact same thing as 3 and 4, but it provides an interesting result that's going to be helpful in the coming slides. So exact same concept. I'm going to FOIL it out. This is what it looks like when I FOIL it out. But notice what happens in that step. The -18i and the positive 18i cancel out, and the I squared becomes a -1. So I've multiplied two complex numbers, and I've gotten a number that's real. I have no imaginary numbers in my final answer of 85. Well, the reason that happens is, I'll go back. The reason that happens is 9 plus 2i and 9 minus 2i are something that we call conjugates. And so we have a conjugate as if we have a real number or we have an imaginary number and we flip the middle sign. Those two things are called conjugates. And the reason those things are so cool is that anytime you multiply complex conjugates, you will always get a real number. You will no longer have imaginary numbers. So when we get into the very last operation that we're going to talk about of dividing complex numbers, we're going to use that concept. Now, dividing is a little bit of a misnomer. I don't really like the term because when we think about dividing, we think maybe long division or how many times a number fits into another number. That's not really what we're going to do. So anytime you see the term dividing complex numbers, now this is a very common problem that I see throughout the course. When we have something like this, when we have a binomial squared, what students typically, well, not typically, but often do is they take that square and they say, okay, I'm just going to take the square and put it on the 3. I'm going to take the square and put it on the I, and then I'm just going to go ahead and square each term individually. That's not correct. That definition of squaring something is you multiply that thing by itself. So anytime you see something like this, a parentheses and a square outside, just rewrite it twice. That's what you're going to do. And then you're going to FOIL it out just like we saw in the previous example. 3 times 3 is 9. 3 times negative I is negative 3I. Negative I times 3 is negative 3I. And negative I times negative I is positive I squared. Now I have to resolve the fact that I is going to be negative 1. And then I can combine like terms. Negative 3i times negative 3i minus 3i gets me negative 6i. And then 9 plus negative 1 gets me 8 minus 6i. Now finally, I'm going to go through this one a little bit more quickly because it's actually the exact same thing as 3 and 4, but it provides an interesting result that's going to be helpful in the coming slides. So exact same concept. I'm going to FOIL it out. This is what it looks like when I FOIL it out. But notice what happens in that step. The negative 18i and the positive 18i cancel out, and the I squared becomes a negative 1. So I've multiplied two complex numbers, and I've gotten a number that's real. I have no imaginary numbers in my final answer of 85. Well, the reason that happens is, I'll go back. The reason that happens is 9 plus 2i and 9 minus 2i are something that we call conjugates. And so we have a conjugate as if we have a real number or we have an imaginary number and we flip the middle sign. Those two things are called conjugates. And the reason those things are so cool is that anytime you multiply complex conjugates, you will always get a real number. You will no longer have imaginary numbers. So when we get into the very last operation that we're going to talk about of dividing complex numbers, we're going to use that concept. Now, dividing is a little bit of a misnomer. I don't really like the term because when we think about dividing, we think maybe long division or how many times a number fits into another number. That's not really what we're going to do. So anytime you see the term dividing complex numbers, really you should be thinking, I'm going to make it so I don't have any imaginary numbers in my denominator. So I have these two complex numbers here. I'm going to divide 4 minus I divided by 3 plus I. Well, I want to get a real number on the bottom. I'm going to use the conjugate. So I have 3 plus I. The conjugate of 3 plus I is 3 minus I. I flip that sign in between the two terms. I'm going to multiply out the bottom, but with fractions, if I multiply anything on the bottom, well, I have to multiply them on the top. So if I multiply out the top, I'll get 4 times 3 gets me 12i. 4 times negative I gets me negative 4i. Negative I times 3 gets me negative 3i. And negative I times negative I gets me I squared. If I replace the I squared with a negative 1 and combine the I terms, I would get 12 minus 7i plus negative 1. And I get 11 minus 7i. Now I'm going to FOIL out the bottom, and my claim was that if I multiply any conjugates, I would get a real number, so hopefully that will fall out. So I FOIL it out. 3 times 3 is 9. 3 times negative I is negative 3i. 3 times I gets me 3i, and I times negative I gets me negative I squared. Well, those middle terms cancel out, and I'm left with 3 minus I squared. Well, I squared is negative 1. So I get 9 plus 1 gets me 10. And that's my final answer. 11 minus 7i over 10 is what I'm going to get if I, quote unquote, divide my complex numbers. Now, if I want to write it in the correct format, we go back, if you rewind to 2 slides back, I believe, the definition is for a complex number is a plus bi. And so I honestly accept the top thing, the thing that I have above my box right there, because that's typically how I write it, and honestly typically how a lot of mathematicians write it. It's perfectly fine. But if we're going to follow the technical term of getting a complex number, we're going to have to separate them. So we would do my first part of my fraction, I would do 11 over 10, that's my real part. And I would do 7i over 10, that's my second part. And then I have a subtractions in the middle. So really the thing above the box and the thing below the box is the same thing. It's just the thing below the box is technically what a complex number is. Now, I claim that we can multiply any imaginary numbers and that operation will still hold and will get us a complex number. Well, if that's true, I should be able to know what I to the third is, or I to the fourth is, or truthfully, I to the 1,000th. That should be something that is either an I or a 1, maybe with a different sign along the way. Well, let's look at the first couple of things. I is I, not really anything fancy there. I squared is -1, we've seen that as well. I cubed is, well, that's I squared times I. So I get -1 times I, -1. And I to the fourth is I squared times I squared. So -1 times -1 gets me a +1. And in fact, I can do that process again, and I would get the actual same pattern. I get I to the fifth is I to the sixth is -1, I to the seventh is I to the eighth is 1. And again, I could do that all the way up to whatever I want to find, 1,000. The issue is that becomes a bit cumbersome because you don't want to run through the pattern. If we do it up to 1,000, that'd be almost like 250 times. It's not really worth it. So instead, there's a little bit of a shortcut to help us so that we can kind of find exactly where our I to whatever power will fall into this pattern. It's either going to be one of these 4 possibilities. So let's look at something like I to the 15th. If I did one more column of this pattern, I would be able to see it. It's not super hard, but let's develop this kind of trick that we're going to use. So since this cycle happens in patterns, or this pattern happens in cycles of 4, what we're going to do is I'm going to take that number, my power, 15, I to the 15, I'm going to divide it by 4. You might want to do some long division because we're really only concerned about what the remainder is. I don't really want to know what the answer is. So the answer is 3, but the remainder is 3. And so what the remainder is going to do is it's going to tell me which part of the cycle I fall into. So if the remainder is 3, that's going to be the same thing as I to the third. So anytime I get the result of a remainder 3, my answer is going to be -I. So I to the 15th is -I. If you wanted to continue the table, you would see that actually does fall out. I to the 15th gets you -I. So let's give you something that you probably wouldn't want to kind of go through the entire table. I to the 104. Same type of process, it'd be 104 divided by 4. Again, long division's a good way to figure out the remainder. There's other tricks online that you can kind of find, but I'm not going to give you anything that would be too difficult to do with long division. And so if we do long division on 104 over 4, I get that my answer is 26. Again, I don't care about my actual answer, I only care about my remainder. So my remainder 0, I look at that table that I've developed on the left side of the screen, and I see, oh, a remainder 0 means that I'm going to have the same answer as though it was I to the fourth. Well, I to the fourth is equal to 1, so I to the 104 is equal to 1. And this process will work for I to any power. It might be a little bit more difficult, especially if you're using long division for really large numbers, but certainly doable. That's the end of this section.